In this video, we will be talking about the sp2 and sp3 hybridized orbitals. When we add together an s orbital with the px, py, and pz orbitals and hybridize the four orbitals, we get back four hybridized orbitals that here are displayed one at a time. When we put all of them together, we get a shape that looks like this. This shape is a tetrahedral arrangement in which our four hybridized orbitals are pointed to the four corners of a tetrahedron. This is what we get when we have an atom with four electron groups around it. The four orbitals are hybridized together to give you those four electron groups, and you result in a tetrahedral geometry. The angles in that tetrahedral arrangement are 109.5 between each one of your hybrid orbitals. The atoms use these hybrid orbitals for all bonding and lone pair. So we have the case here of methane, CH4, where you have carbon in the center and four methane groups. The carbon atom takes on an sp3 set of hybridized orbitals in order to bond with the four hydrogen. Another example of an sp3 hybridized orbital would be nitrogen in an ammonia molecule, NH3, where you have a lone pair of electrons on the nitrogen that get put in one of your sp3 hybridized orbitals. The other orbitals, which each had one electron in them, are able to bond with three hydrogen atoms to give you the trigonal pyramidal shape, which belongs to the tetrahedral electron geometry. If instead of hybridizing our s with all three of the p orbitals, we instead hybridize an s with two p orbitals, we result with the sp2 set of hybridized orbitals. Atoms with three electron groups around it are signatures of sp2 hybridized orbitals. This hybridization takes on a trigonal planar system. You can have your carbon being trigonal planar. Sometimes nitrogen will take on a trigonal bent or a bent molecular geometry within the trigonal planar electron geometry. The bond angles will be about 120 degrees apart, and the sp2 hybridized orbitals take on a flat shape. An atom uses hybrid orbitals for the sigma bond, which is your single bond, and a lone pair, and uses non-hybridized orbitals, your p, to form a pi bond, as we will see in a subsequent video. So looking at the orbitals as they hybridize together, we can have an s orbital with two p orbitals. This would leave an unhybridized p orbital, which could then be used for, as we will see shortly, pi bonding or our double bond. So taking one s, two p's, hybridizing them together, you're hybridizing three orbitals together, so you get three hybridized orbitals back. Remember, how many ever of the standard orbitals you put together in your hybridization, you get the same number of hybridized orbitals back. So we have three hybridized orbitals that are degenerate. They each have the same amount of energy, and we retain our one unhybridized p orbital that we didn't mix in for hybridization. So when adding together a spherical s orbital with two p orbitals, in this case the px and the py, we end up with a planar set of hybridized orbitals. We wouldn't have anything extending into the z-axes because the px and py sit directly along the x and y axes. So when we hybridize the orbitals, summing together the wave functions that give us the shape of these orbitals, we would not expect to have anything extending into the z-axes, which is why the resulting sp2 hybridized orbitals are planar.